Alright, so now that we know the sort of basic function of writing an ionic compounds formula and then naming it and then being able to go back and forth, now we're just going to start throwing in new types of ions. But those fundamental systems aren't changing. It's name of cation, name of anion. It's number of cations, number of anions. They sum to 0 charge. So it is a neutral unit of charge. Like when we write that formula unit, we write it all out. When we write that whole formula, it zeroes out the charge. So all of that holds. So all that we're doing now is just understanding how to work with a couple new types of ions within those processes. And so the first one is the transition metal ions. That's what I'm going to talk about here. And then I'll talk about polyatomic ions next, slash last, I guess, because it'll be the last video for this section. So, transition metals, as you remember, are in the middle of the periodic table. And so what's the problem with transition metals? Well, problem number one, periodic table doesn't tell us anything about what their charge is going to be, at least not in this class. You can take general chemistry and then you can start to be able to at least make educated guesses at it. So, you know, if we look at like lithium and sodium, potassium, so on, we know those are going to be a +1 charge. They have one stable ion and it has a +1 charge. They have one option. Magnesium becomes a +2 charge. That's what it does. Same with beryllium and calcium. You know, this whole column here becomes, you know, +2. Aluminum, boom, 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 +3. Halogens, -1. Oxygen, sulfur, so on and so forth, -2. We can work the edges of the periodic table. We're emptying valence shells, we're filling valence shells. Transition metals kind of land outside of valence theory, so they have a lot more complicated stuff going on with how their electrons are positioned, beyond your simple idea of a valence shell. You have to get into what's called atomic orbitals for that, and we aren't going to do that. So, you know, I always talk about how valence theory is alright for the first 20. First 20 elements, it works. You hit element number 21, it all blows up. And you can kind of cheat a little bit over here, and you kind of cheat over here, and you sort of, you know, ignore the middle. But we can't, because that's exactly what we're talking about here. So the first problem is just that the position on the periodic table, it just doesn't tell us anything about what the charge is going to be. And that's not great, right? We really like to use that tool. You know, it's not going to help us figure out what the charge of the ion is. Which kind of, you know, that was our go-to move, right? What's the charge of a magnesium ion? Well, I look at my periodic table. What's the charge of a oxide ion? Which now you know what that name means. It just means oxygen with a negative, boom, 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 2 charge. Alright? So that's problem number 1. Problem number 2. This one might seem a little bit weird, but every ion we've worked with so far, like if there's a sodium element, no charge. 11 electrons, 11 protons. There's a sodium ion, +1 charge. 11 protons, 10 electrons. That's the only ion sodium's going to be that's stable. If it's anything else, it's going to pick up or lose electrons to get to that +1 state. And it's going to do so aggressively. But transition metals can, and most of them do, have multiple stable ions. And what do I mean by that exactly? Well, let's look at copper, right? If you've ever seen, you know, copper jewelry, copper plumbing, a penny, which is actually, so pennies now are kind of like, I guess not, it would be like an Oreo cookie if the outside was all sealed in cookie, because it's zinc in the middle. They cheated. For a while there, they were solid copper, and I forget what year exactly. They started filling them with zinc because zinc is a lot cheaper than copper, so it's copper-plated zinc, and they still cost more than 1 cent to produce. So they're like, last I remember, it was like 1.2 cents to make a penny, which seems ridiculous, right? No one, I think our society could survive without pennies at this point. Mostly they're just used to drop on the ground so someone can find them for good luck. I don't know. Fill a jar so you can take it to a Coinstar and they eat 10% of what you turn in or something like that. Coinstar would suffer. The rest of the world would be fine. And I'm good with that, to be honest. So, Copper is a transition metal. Okay, so it's in the transition metals, and it can have multiple charges. So you can have copper. The Romans knew about it. Good old cupric. And you can go two directions with this. It can be +1 ion or a +2 ion. So it has options. Like sodium could only be a +1. Magnesium could only be a +2. But copper can be either one. Now, when we talk about naming things, one of the very important details is one name, one compound. Right? So, you know, if we mix this with the chloride ion, we get two different formulas. Because this is a +2, chloride's a -1, so you need two -1s cancel out. So you get CuCl2. But over here, it's just 1 to 1, +1, -1. That zeroes out the charge. So what do we call these? I can't call this the copper ion and this the copper ion, right? Because then I'd have copper chloride. Well, which copper chloride are we talking about? I need one name, one compound. You know, it's like you have to be able to play a game of telephone with this. So, we develop a system. And it's, as usual, we didn't get creative. So this is good. We didn't get creative. It's bad. It's bad when we get creative. So if you had to take a second and just think about what you might name these ions. Alright? What's different about them? What could you name them to make that difference clear? Well, maybe you guessed, maybe you didn't. But I'm going to write them over here so I can write the names with them. Cu+, we call this copper 1. If you guessed that it was the number, good job. And what that means is we use Roman numerals because we can't make it too easy for you guys, right? Got to make some challenge in there. If we can't work Latin in, well, we can work in their number system in copper 2. So it just tells us the charge. Now, technically, what we're actually labeling here is the oxidation number, but guess what? That's the same as the charge for these metal ions. So we don't have to worry about fancy words like oxidation right now. So copper 1, copper 2. So guess what we name this, right? It's name of cation, name of anion. Well, this is copper 1 chloride. And this is copper 2, I'm going to write it down here, chloride. Let's run out of room. And so they have different names. So I can say copper 1 chloride, I can say copper 2 chloride. And people will know what I'm talking about. You know, they won't put the wrong copper chloride in my baked goods or whatever I'm ordering with it. So, because you don't want cupcakes with copper 1 chloride in them. That's just, whew, those aren't birthday cupcakes at all. You need copper 2 chloride for that. Okay, so we have this naming system. So there's a couple pitfalls here. You're only going to use Roman numerals when you have to. You don't use them all the time. So it's not like you have the magnesium 2 ion. You just have the magnesium ion. There's only one. We are lazy. We are lazy, lazy, lazy. We're only going to use extra stuff like Roman numerals and numbers when we have to. So when do we have to? When you're dealing with a transition metal that can have multiple charges. Alright? So we're only using Roman numerals when we have to. And that means when we're dealing with transition metals that can have multiple charges. So that with multiple, we'll say multiple stable ions. They're always going to be cations in this class. I don't like to lie to you guys too much, but also I'm not going to complicate things. So that's one point I should make. When you're dealing with these transition metals, metals are cations. So they're still all going to be positive charge. It's just that you might have a situation like copper where it's +1 or +2. So how do you know? How do you know to use the Roman numerals? Well, what this means is that you use them with every transition metal except for a couple. And I'll tell you which ones here in a second. Now there's actually a couple others, but I don't expect you to know them all. So we are going to have silver, and that's because it only becomes silver plus 1. So you just have to remember this. And then zinc becomes just zinc 2 plus. There's no other option. And I like to throw in, even though we've already talked about aluminum, I like to throw that one in as well for a very cool reason I'm going to talk about in a second that defines my entire teaching career. Okay? So everything else gets Roman numerals. Alright? In this class. You can look up and see that maybe there's a few others that don't. I'm not going to make you know those ones, alright? Man, that's some clean looking handwriting right there. Look at that. That is some fine quality. People are always like, you should have been a doctor. Write some prescriptions that kill somebody. Alright. So, if you don't know what I wrote, every transition metal except for silver, which becomes silver plus, zinc, which becomes zinc 2 plus, and aluminum, which becomes aluminum 3 plus, which we've talked about before. It's not really a transition metal. These get Roman numerals. But why did I bring aluminum into this? Why would I sully its good name? Well, it's the stairway of ions. So you can actually use your periodic table +1, first step, +2, second step, +3, third step. And now you know the stairway of ions, which is not at all named after Stairway to Heaven. I want to be clear about that. This is stairway of ions. You know, you're climbing a stairway of ions. Alright? Nothing to do with the song. So, +1, +2, +3. Everything else in here you can assume has multiple charges. If I were to give you one that doesn't, I'm gonna eat the points on that. Alright, that's my fault. So I only expect you to know silver's a +1, zinc's a +2, and aluminum's a +3. Everything else needs Roman numerals. Alright? And so we're gonna put this into practice now. So I've introduced the problem, I've introduced the solution, but let's make sure we understand how to apply it. Alright? So let's look at an iron compound. So iron is a transition metal, dead center in the transition metals. So the periodic table will offer us no help at all. But when it comes time to write the formula from the name, I can just be like, oh, well, maybe I have, whoops, I can spell iron, I swear. We'll say iron 3. So iron can be a +2 or +3. It's, you know, another one of those transition metals that, you know, has some options. So we're going to say this is iron 3 oxide, also known as rusted metal, you know, rusty iron, that red flaky stuff, or powder. Alright, so we got iron 3 oxide. Okay, how do we write the formula? Well, we've got name of cation, name of anion. We know what oxide is, we've dealt with this before, right? This is just on the right hand side, good old fashioned -1, -2. Alright, so this is an O with a -2 charge. We've seen this one a few times, but iron 3, okay, well, we can use the periodic table to help us out with one thing. Chemical symbol for iron is Fe. I'm sure you all memorized that in Latin class, but just in case, okay. But how do we know what the charge is? Periodic table doesn't tell us, right? Periodic table is no help here. It gets us this far. But what do I have right here? That's the charge. The name just tells it to me. In some ways, it's easier. Alright? And then guess what I do? We're going to write the formula. Okay. So I'm going to have Fe2, do our little switchy switch here, O3. 2 and 3 don't have a common denominator, so I am done. Alright, so I don't have to remember any tricks of the periodic table to figure this information out, because it's right here. Now, be aware that if you see something like zinc oxide, I didn't write a Roman numeral. Why didn't I write a Roman numeral? Because I expect you to remember that zinc only has one stable charge. And let's see, there's step 1 and step 2. It's on step 2 of the stairway of ions. Not that I'm like pushing my own, you know, pedagogy or anything. Super hard. The whole world, like I'm going to write a textbook just about the stairway of ions. So we just know it's zinc. We look, okay, 2 plus, It's the middle of stairway of ions, or you just memorize it. I don't know, maybe you got a cool tattoo for it or something. And zinc is Zn. We get that from the periodic table. And oxide, we've been over this one enough. We just know it's O2 minus, but we can use periodic table to figure it out. We do the little switchy switch. I get zinc 2, O2, which has a common denominator, so what I actually get is ZnO. So be aware that 2 and 2 have a common denominator of 2, so we gotta knock that out. Alright, so the name to formula isn't so bad. What's tricky is when we gotta go the other way. Let's say we have a formula. Alright, let's see, we'll use copper this time. We'll go with Cu. Well, let's see what we'll do. We'll do Cu3P. It's not like I like spelling words or anything. I'm totally not just trying to spell cup here. Okay, so what do we do? What do we do? You have to do a little detective work, right? You don't have to know what the charges of copper can be here. Like I talked about how it could be a +1 or +2 before, but what we do is just have no idea, alright? But we do know what the anion is. We will always know what the anion is, alright? We look at our periodic table. Phosphorus will become a -1, 2, 3. Okay? And so what we have is 3 times some unknown charge plus -3, just one of them, is going to equal 0, right? This whole thing has to add to 0. So these charges, this copper with an unknown charge, could be +1 or +2. We know that much, and you don't even have to know that much. Alright? And so then we just solve, and we go, okay, well 3x equals 3. I'm just going to add 3 to both sides. X equals 1. Alright, so this right here means that we have copper +1. Alright, so we've done some work. We're not done. We've got to name it still, right? So what's the name of this? Well, name of the cation. What's the name of this cation again? It's copper with a +1 charge, so we got to write the Roman numeral 1 because it's not silver, zinc, or aluminum. So we got to write the Roman numeral. And then phosphorus becomes phosphide. That's it. So going from formula to name is a little trickier, but you just hang in there. All right. So we'll do one more here. We'll go CR N2. Okay? This is what we'll do. Alright. So, we can sort of start to sketch this out a little bit. You're like, what is CR? What is CR? We look, there it is. That is chromium. Alright? It's going to need Roman numerals. I don't know what Roman numerals yet. And then N is nitride. So, we've got to figure out these Roman numerals. So this is the trick. Alright? We know what nitride is because our periodic table will help us out there. So it's -1, 2, 3. Really like those -3s today. So we have that with an unknown charge on our chromium. So I'm just going to call it chromium X. Sounds very comic booky, I know. Alright, and so we have X plus, because we only have one of them, 2 times -3 equals 0. So we got to set that up. So we know the charge is going to be 0. We know our anions create a -6. Our cation has to offset that. So we solve this and we get X equals 6. Which means we are dealing with chromium with a 6+ charge. And I didn't choose this one on accident. This is a very famous ion. This is hexavalent chromium. If you've ever seen the movie Aaron Brockovich, which was filmed in Boron, California. That's right. Yeah, that's right. They're very proud of that in their museum I went to and bought that shirt. This is what poisoned the community. This is, yeah. So it's great they filmed the movie there. It was actually the town next door. So the town next door gets poisoned by hexavalent chromium getting leached in their groundwater from, I forget, some sort of facility. And then it's the town over that already has all that borax money. They're the ones that score the film. Like, what justice is there in the world, you know? Oh, man. I can't remember the name of the town. I drove by it, but I can't remember the name. Unfortunately for them, that whole area of the desert looks identical, so you wouldn't know they didn't film there. I don't think many people live there anymore anyway, on account of the fact that their groundwater got poisoned. So, you know, sometimes environmental laws can be very beneficial to communities. Especially when they're followed. Okay, so, Roman numeral for 6. What is that? Well, you know, I always struggle with this, but it's VI, unless I have it backwards, which I don't. Okay, so chromium 6 nitride. That's what we're working with here. Alright, so that is how we handle these transition metals. You got two problems. One, periodic table, no help. Two, they've got options. Even if you did know from the periodic table, you don't know, because is it a +1, a +2, +3? It could be anything. Chromium could be a +6, a +3, or a +2. You don't have to memorize that. All you have to do is be able to sniff it out from the formula here. Put on your detective hat, do a little bit of math, or when you're dealing with the name, guess what? I've already told you what the charge is. So that going back this way isn't so bad. So there's a reason I did so many examples going left to right here. But if you have to go back the other way, you got the name of the ion, it's going to tell you the charge right in it. So it's not so bad. Except for silver is going to be a +1, zinc a +2, and aluminum a +3. So I'm not going to give you those ones in the name. There will be no Roman numeral. So I won't give you a Roman numeral, and when you write the formula name, you don't give me a Roman numeral. That's all you got to remember with those. And that, you know, what the charges are going to be every single time with the ions. Alright, so this, like I was saying, this is just like what we did in the first two videos. We're just adding details to it. So now, really the detail we added is the Roman numeral. And that lets us work with a lot more of the periodic table. Now we can get all of these metals in there. Okay? So there's one more type of ion to talk about. And these are actually going to be made out of multiple atoms. So they're polyatomic. That's why they have the name. And so that's what we're going to talk about next. And again, all the same tricks, just new details getting folded in.